Hey guys, welcome back. In this video, let's go through the code for variational autoencoders using keras on MNIST dataset. And in the last video, if you haven't watched it, I highly recommend watching it. In the last video, we talked about what variational autoencoders are. And let me spend a couple of minutes in case you haven't watched the previous video, just quickly talking about what we are trying to do right now. So autoencoder is where you have an input image and an output image. In this case, I added sunglasses to Mona Lisa because we are varying Mona Lisa by adding information about sunglasses. This application we're going to do today is not that cool. We are going to do MNIST for now, but this is just an example of how you can modify a latent vector, okay, to give you slightly different results. Now, I'm replacing this latent vector with a normal distribution, let's say, okay? And that distribution is defined by two parameters. One is the mean, and the second one is the standard deviation, right? So when you have a normal distribution, you can define it using the mean and the standard deviation or variance, if you want to call it. So once we have this distribution, then we can sample it. The Z stands for sampled latent vector. So instead of having a fixed latent vector, we're going to sample it from this distribution. So this is where variational part comes in. So every time you take this sample, it's random. Well, you can define it, but if you randomly select it, then you're going to get slightly different result when you perform your decoding operation, which is basically a generative operation that you're trying to do here. Okay, so that's the summary. Basically, your standard autoencoder, where you have a latent vector, is updated by using mu and sigma, mean and standard deviation. And during the training process, these get updated. Okay, mu and sigma, and then the sample you're always randomly sampling. So this is not going through the training. The weights are not updated for this one. Okay, and also I mentioned that. Okay, now. Here is how it looks like. I mean, in terms of reparameterization trick, how are you going to define this during backpropagation? So what we are going to add a layer, okay, with these two parameters that we wanted to learn. And we'll go through that in the code right now. So I hope this serves as a quick summary. If not, please watch my previous tutorial. Now let's jump into the code. MNIST data, we have worked with this quite a few times in the past if you are a regular to my channel. Otherwise, it's basically a bunch of handwritten digits, right? And these are all just images. When I say handwritten digits, these are all images. So let's first import all the required libraries. So I'm going to import keras, and I'm also going to import from the layers the convolutional 2D and transpose, because we'll, again, autoencoder, right? So you downscale and then you also upscale. So 2D transpose is going to help us do that. And others should be pretty straightforward. Input, the flatten layer before it goes into dense, and then lambda for lambda layer is very important if you want to do some math within this, within your model. So lambda helps us do that, and reshape and so on. Everything else should be pretty much straightforward. And of course, the MNIST dataset, you can download it if you want, but keras.datasets already has it. So let's go ahead and include that. Okay, so let's go ahead and run this. Now, the MNIST dataset, when you unwrap it, MNIST.load data, it's going to give the first two parameters as xtrain and ytrain, and the next two xtest and ytest. So let's go ahead and run this. You should see xtrain 60,000. And where is my xtest? 10,000. So there are 60,000 digits, images, each image 28 by 28. Okay, and they're all integers 8. And then the y is basically what is that digit, right? So you probably know what this is. Is it 7? Is it 2? Is it 1? What is that handwritten digit? Okay. So now, first thing first, we normalize this because these are all unsigned integer 8s, meaning the values of each image are going from 0 to 255. So let's normalize this to the between 0 to 1. You can use any type of standard scalar normalization. In this case, all I'm doing is just divide by 255 because I know all my values are between 0 to 255. Of course, if you have multiple streams of data where they have different ranges, you can try min-max scalar or some other type of scalar. So this is pretty straightforward. Just dividing my x values by 255. Obviously, you don't do that with your y values, right? I mean, they are just labels. Okay, so now my x test and x train, you see the dimensions are 10,028 by 28, 60,028 by 28. But let's go ahead and reshape it so they're at an appropriate shape for my, where is this image width? For my, when it goes into my neural network, okay? So all I did is just image width and height. In this case, it's 28 by 28. I'm not sure what images you're going to work with, so I just, created new parameters for that. Okay, and the number of channels in this case is equal to 1, again, because MNIST data, it's all grayscale images, so it's 1. If you're working with color images, RGB, it would be 3 channels, okay? So for now, this is going to be 1 channel. Okay, now let's reshape it. And how are we reshaping it? So here it's 60,000 images, 28 by 28 by 1. 1 represents the channel. If you're reading color images, that will be automatically defined most of the time, but still make sure that is the case. Okay, so now we have our input shape to be 28 by 28 by 1, okay, and we have 60,000 images for train, 10,000 images for test. So far, no tricks. And also, just in case you're curious, let's just view a few images. So let me go ahead, and I always do this. I don't know why, but I like to see things before I proceed to the next step, okay? So you can change this. I mean, I'm just checking, whatever, 40-second one, which happens to be, see how I love the number 42, 420, 4200. So, but anyway, so if you want 40, I don't know, 12, whatever that number is, so you can go ahead and look at it, and it's number 3. So these are all a bunch of handwritten digits, okay? Let me change this back to 42, otherwise I cannot sleep. Okay. Now, let's come down to building the model. We are ready. We have our input ready. That's it. That's why I like to work with MNIST on new things, because you don't have much to do other than expanding dimensions. That's pretty much it. Okay, now let's focus a bit. What do we have here? So let's get back, and we have encoder, the left-hand side, decoder, the right-hand side, and the central part where we need to define our mu and sigma, and z, which is the sampling every time that you do this. Okay, this is the only tricky part. Otherwise, it should be pretty straightforward. So let me get back. Okay, so first of all, let's define our encoder decoder. And by the way, sorry for going back here. How many, let me move this. The latent vector right here. What is the dimension of latent vector? What do you want that dimension to be? How many numbers? Is it 2 digits? Is it 10 digits? I mean, obviously, if you encode your image into only 2 digits, it may get a bit blurry when you decode it. If you have like 10 or 20 digits, then it will be sharper when you decode it. But the problem is now you have 10 or 20 digits in the middle. So it's up to you. Anyway, so let's use latent dimension equals to 2, which is very customary for, let's say, MNIST type of data. I think because it's only 28 by 28, even any loss of information, it's not that apparent, okay, with latent dimensions of 2. Okay, so now let's define our encoder. This is pretty much straightforward, not much going on right there. So all I'm doing is, okay, you have your input layer with whatever the input shape is, 28 by 28 by 1, right? We just defined that. And well, I like to label, I like to name them. So when I print the model, it's easy for us rather than looking at random names. Okay, and then we have 4 convolutional layers, 32, and then 64, 64, 64. Again, you can experiment with various types of these convolutional layers, okay? Especially when it comes to other examples. So this is we're not done with encoder yet, because we still have a few things before we get to encoder. We have to define the dense layer, and sorry for this, we have to define this part in a minute, okay? So before getting there, I would like to just save my convolutional shape up to this point, whatever happens. What is my convolutional shape? My convolution shape up to this point is, you see up here, 14, 14, 64. And how many other images, right? 14, 14, and 64 after these operations. Why am I doing this? Because when we get into decoder part, I want the shapes to match. After the encoder and before the decoder, I want this input shapes to match, okay? So we are extracting this, that's it. And then, okay, my X, now I'm going to flatten it, okay? Did we run this? No. and then I add a dense layer right here. Okay, and now let's define the two parameters mu and sigma. Okay, for z. Okay, I did z mu because we are defining mu and sigma. This is our distribution, and these two are exactly the same. If you see down here, these two are exactly same. I'm defining as these two because these two are independently learning. Okay, so this is basically our dense layer with how many dimensions? 2, right? In this case, our latent dimension, we defined this as 2. So dense layer with 2, dense layer with 2 nodes. Okay, that's it. So this is our, and let's go ahead and run these two. I'm going to share this code with all my notes and everything, so you can go through this at your own pace, but hopefully right now you're paying attention to this. Now comes the reparameterization trick. So far we defined up to this part. Now comes the reparameterization trick, okay? We talked about this in the theory part. Okay, so reparameterization trick is, again, we are defining a sampling function with mu, and how did we define this? Sorry, how did we define this? Or z is mu plus sigma times our epsilon, where epsilon is this normal distribution. Okay, so that's exactly what's going on. So here, these two, okay, and the output of this function is going to be your mu plus epsilon multiplied by sigma. Well, sigma is, this may be a weird way of defining, but sigma is your k exponential z sigma over 2. Okay, so this is, in a way, as you can see, this is related to sigma or variance, if you want to call that. Okay, so this is the reparameterization trick. So let's go ahead and do that. And this allows us to, by the way, why are we doing this? This allows us to train both mu and sigma during the training process. Okay, so there you go. And I'm pretty sure none of this makes sense at the first time you're watching this, but if you watch this a few times and also read a lot of amazing online blogs or other videos, you'll probably get enough information to piece everything together. That's how I learned, basically. Okay, so once that part is done, now we have to sample it. So how do we define the z? How do we define, let's get back, the z part? We have to sample it. Okay, so now is our sampling part. So this is where I'm just using our lambda function, okay, where it's the output shape is just the latent dimensions, because we are sampling a vector. And what is the dimension size? And what is the size of that? Again, latent dimension, which is 2. That's pretty much it. Okay, and let's go ahead and run this line. And finally, we are kind of almost, this is the last layer, in fact, of our encoder. Okay, so the encoder is ending right around here. Okay, so based on what we're defining here. And then comes decoder. In fact, you can say, okay, encoder ends there. But anyway, so now let's put together the model for encoder. Okay, we defined all these layers. We have to put everything together, right? So we haven't done that. So how are we doing that? So our input is like input image, right? When we put together a model, you have input and output. Input image is the input. Output is your mu, sigma, z. Okay, so input image is your input to the encoder, and the output of the encoder is mu, sigma, z. I hope things make sense, at least on the first level. Watch it again and again and again, practice. Eventually it makes sense. Okay, so let's go ahead and run this line, assuming I have executed every other line, and let's go ahead and print out our encoder. Let me expand this side so we can see it a bit better. So what do we have here? An input image, 60,000 of them, 28 by 28 by 1, right, going in, and then they're going through these convolution layers, the 4 of them, 32, 64 features, 64 and 64. That's the output, and we added a flatten layer. Remember, we added a flatten layer right there, and then comes the dense layer with 32, and then comes the mu and sigma layers, each with 2 right here. That's pretty much it. And finally, the z right there. Look at this value, this number right there, 0. What does that mean? That means the total number of parameters. It's 0. It's not training on this, because we are just sampling from the z. Okay, and here it's actually training on these two. Okay, so that's pretty much it up to that point. And now, sorry, let me resize. Okay, so now let's define the decoder part. Now decoder takes the latent vector as input, right? So the decoder's input is z, the latent vector, the random sample latent vector. So let's go back. So there you go. The shape of that is latent dimension, obviously. Okay, and then we are going to add a dense layer, and then remember this convolution shape that we kind of figured out. What is the convolution shape right there? I think it was 1464 or something. So that's the convolution shape right there. The reason why I got that is up to the encoder point, we kind of went from 28.1 to 14.64, and then we flattened it. So now the point is I want the decoder part to go from 14.64 all the way to 28.1, right? So we have to reconstruct the original image back. Okay, so that's why we are taking that as input and taking the 3 dimensions, 1, 2, and 3, and multiplying them to make sure that, okay, when we reshape them, when we are going up, the output image, the math works out. Okay, where we get our 28.28/1 or whatever that output image is. If not, if you just put some random numbers, then you'll not get the same size output image. And I did this mistake many times. Okay, so that's what this part is, and we are reshaping it. And where are we? Sorry. Okay, so let's go ahead and run these lines of code up to this point because we talked about it, reshaping it to that shape. And now we have to do the upscaling part, right? I mean, we are doing the transpose. This is like regular autoencoder. You did the encoder part, now decoder part. So instead of conv2D, we are doing conv2D transpose. So let's go ahead and do that. And this is the final 2D transpose that gives us number of channels is 1 in our images, right? 28.28/1. So eventually we will get 28.28/1 as output. Hopefully when we do the decoder.summary, that's what it should give us. Well, actually, we'll get there in a second. So our decoder, again, just like encoder, our decoder should have like an input, output. So the decoder input is the input that's going into decoder input, right? The one we defined up here. And then the output is our X, basically, the decoder output. Okay, so let's run this and look at the summary for decoder. So we put together encoder and decoder, and then we'll put everything together, like sandwich everything together in a minute. Okay, so the decoder input, there is like no trainable parameters over there, and then we have a dense. We are going from 14.14.64 to 28.28.32 to 28.28.1. Okay, so everything works out. Encoder input 28.28.1, decoder output 28.28.1. So sanity check, everything is fine. Okay, so now what? So now this is the part that can be done many ways, and this is the way I liked it. Again, parts of this is inspired by me going through a lot of code on GitHub, and I like some part somewhere, I like some part somewhere. Some people make what should be a simple code very complicated. I kind of stay away from that, but I take that and then convert that into something that's easy for me, and that's what I'm presenting to you. Okay, so there is some stuff that I got from somewhere, but it's all a fusion of things I got from many places, because I haven't invented variational autoencoders. So everyone copies from somewhere. It's called inspiration from somewhere. Okay, so what am I trying to do here? I think I sometimes talk too much and I forget where I am. Anyway, so we are applying the decoder to our latent sample. Remember, we are getting this sample here, Z. Now I'm trying to apply this decoder onto my Z to get the output. Okay, so that's exactly what I'm doing here. Z decoded is basically applying that onto Z. Okay, now comes applying the custom loss functions. Remember, again, sorry for going back and forth, custom loss function, because the loss function is reconstruction loss plus KL divergence loss. I talked about this in the last video. Okay, so this is basically a separate class. You don't even need to define a class if you don't want to, but again, there is a custom layer we are actually adding because we are training on these parameters. So the custom layer here is it contains reconstruction loss and it contains KL loss, and what it returns is the mean of these two losses. That's it. Okay, reconstruction loss is basically binary cross entropy. Okay, this is what we use for regular autoencoder. So reconstruction loss is nothing tricky. And KL loss, again, where did I get this from? Again, there are many ways you can actually do this. I think Keras also has a KL loss built-in method, but I haven't tried it, so go ahead and try that. But anyway, so we are using reconstruction, KL loss, and we're just returning the mean. That's it. That's what this loss returns. And here we are calling it, and we are applying that loss right here on our X and Z decoded. What is X and Z decoded? That's right there, your input, and then the Z decoded is your decoder applied onto your random sample. That's what this part is. Okay, so let's go ahead and run this, and let's put everything together in a second. There you go. And now let's actually define our Y. Again, this is, like I said, there are many ways. You'll see, like, some people actually, instead of doing this, they'll just fit this to X-train versus something else. Okay, but this is the way I thought was the most intuitive for me. So Y. What are we trying to do here? Now we are applying this custom loss to, basically this custom layer is your input image and Z decoded right there. So in other words, think of this Y as your original image after it goes through this encoding, okay, into mu and sigma, okay, and then decoding sample Z values, okay. So this is what we are going to use as, I think later on, where is my Y? Right there. This is going to be used as the Y values for my model. Okay, so that's what I'm kind of separating down here. Again, so Y is the original image, which is my input image. Okay, after encoding. Okay, so original image after entire process, after coming through the other side. That's what my Y basically is. Okay. So that's what I tried to put this in English. Right now I'm reading it and I'm like, maybe I could be a bit better in writing it down. But again, this is very important. So the Y is basically what shows up on the other side after this process happens. That's pretty much it. Original image, encode it, goes through this, randomly sampled, and use that random sampled to decode it back, and that is my Y. That's it. Okay, I'm not going to repeat it one more time. So that's my VAE. My VAE, or variational autoencoder, I didn't run this line, is basically, I'm using the model method from keras, X values as my input image and Y values as the Y that we just did. So I hope this makes sense. Okay, there you go. Now let's go ahead and compile this. So far we just defined the model. Let's go ahead and compile it, meaning what optimizer. Again, you can use a couple. I'm just using Atom, which seems to be the most, how should I say, the one that works most of the time for me. So if I don't know anything, I'll just do this. And I put loss equals to none because it's part of one of my layers. So it's going to be trained on anyhow right there. So let's go ahead and do that. And finally print out the summary. Let's look at the entire thing one more time before we fit it. Okay, so where is it? So this is the input, encoder input 28 by 28 by 1. We go all the way to 14, 14, 64, and then we have the flattened layer. We have the dense 32, and then mu and sigma as these two, and then the Z. We have mu, sigma, and Z, but Z is not trained, okay? Z is not training, we are just sampling it. And then comes our decoder model, all the way going back up to 28 by 28 by 1. And we added our custom layer right here, 28, 28 by 1 right there. Okay, so that's pretty much it. What do we have next? Let's go down and go ahead and fit it. Okay, so let's go ahead and fit it on the X-train values, and let's just do 10 epochs. This can be slow on my system because, again, I'm not using GPU. By the way, I should have mentioned I am testing this on sorry, I already imported keras, so let's just do this. Keras okay, keras 2.0.8. I think it uses GPU, and still it's it also works on 2.4, and you can run this on Colab, no problem. Okay, in fact I tried that, but let's go ahead and do 10 epochs on these many images and see how that works out. I'll pause the video and then continue after it's done, because each epoch is going to take about 1 minute. Okay. Okay, so finally, after about 10 minutes, this is done. So now let's see what we need to do. First of all, if you look at the encoder, let's go back to, where is our encoder? So the output of our encoder, sorry, let's go ahead and see. Yeah, so here, what is the output of our encoder, right? So the input is input image, okay? And the output is mu, sigma, and z, okay? Mu is the mean. Let's just look at the mean distribution, and then each of this, actually how many parameters do we have? Like for each of this, 2, because our latent space is 2. Again, I just want our latent dimension has just a size of 2, that's it. Okay, so now we can look at mu, we can look at sigma, we can look at z, like what the sample, but let's go ahead and look at the mean of all of our distributions and then just plot them to get a good sense for, okay, for in our MNIST data, we have handwritten digits of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So where do they fall in this space? Okay, so let's go ahead and do that. Let's go ahead and plot that. And that is the plan down here. So when you apply encoder.predict on the test dataset, not on the train, now we're doing it on the test dataset, it's going to return 3 things: mu, sigma, z. Let's only look at mu. And each of this is what? 2 values, right? 0 and, 2 digits, I should say, or a size of 2, sorry. So that's what we are trying to do. All we're trying to do is extract mu and then look at the 0th and 1st, okay? And just go ahead and plot them using on X and Y. That's pretty much it, okay? So let's go ahead and plot it. Now you should see this plot that shows this beautiful picture. Let's open this up, okay? And here is the scale. 0 is in blue. I think it's that blue. And green represents our value 9, 8 is somewhere in between, and so on. So, and the dimension here, this is the latent space. Yeah, this is where we are constraining all of our values. This is not looking like a square, but this is supposed to be a square. You see, -4 to 4, -4 to 4. I should have just defined my image figure size as 10. That's why it's not showing up as square. Sorry about that. And let's go ahead and do this. Hopefully this will be a bit more squarish than before. Okay, there you go. So this is it. So why do we now, when we sample, you see the gap right here? This is not continuous. If I pick a value in this gap, it's not going to look that good. But if I pick something right here, so let's pick something around, what is this? -3 and 0, -3 and 0. So let's come down here and let's pick something that's, this is the vector I'm giving it. Now I'm providing a latent vector. If I don't know this space, I don't know what values are good. Now I know that space. Now I know that -3 and 0 mean something. Well, it should mean, I think it's a value of 1. It's tough to see the color difference. I believe it's a value of 1, but we'll figure that out, okay? So my sample vector in this case is -3 and 0, and I'm just giving that to decoder, okay? Predict on this sample vector, and then whatever the output is, I'm reshaping it and plotting it. That's it. Very simple. Now I'm generating stuff, okay? Let's go ahead and do this. Yeah, value of 1. How predictable, right? Let's pick something else. Let's pick, it's tough to find this reddish area, but let's say -1 and 2, maybe. Okay, let's do this. This is fun. -1 and 2. Let's do exactly the same thing again. And now what do we get? A value of 5. So -1 and 2. Yeah, that seems to be a value of 5 right there. You see? Now what happens if you pick somewhere in the transition, right? So this is the tough one. Let's say this is 1.5. 1.5 and 1. I think this will be between these two. 6 and maybe 0. You see, the blue is 0 and this is 6. So what did I say? Positive 1.5 and 1. Let's try that. 1.5 and 1. No negative values, right? So 1.5 and 1. What do we get now? Something that looks like 0 or a 6 or in between. Oh, that looks like 0. So we kind of sampled. 0 is somewhere over there. So what if we just change this a little bit to the left? Let's put 1 instead of 1.5. Okay, It's a continuous. You can put 1.1, 1.05. It doesn't matter. You can put any of those values. Let's go ahead and do that. You see how it's going from 0 to 6 now? Slowly. Yeah. So if you just change it from 1.5 and now let's go to 1.2. Now it goes from 6 to 0. This is what variational autoencoders is. You see now it's slowly moving towards 0. If I move this towards 0.8 or something, it'll probably more towards 6. There you go, more towards 6. I hope this makes sense. So instead of doing this one by one, that's what this beautiful picture that you always see is. Let's go ahead and go from, where is this space going from? -5 to 5, right? Or -4 to 4. Yeah, let's go from -4 to 4 instead of -5 to 5. Okay, the space -4 to 4, and y also is going from -4 to 4. So let's go from -4 to 4. And how many points shall we do? 20 points. Okay, so -4 divided by 20 to 4, -4 to 4, 20 data points. That's what I'm trying to say. And then let's generate this and plot it. That's all I'm trying to do here, basically. Okay, so we are just converting this space into like these parameters, taking the coordinates and then, you know, your x and y coordinates, and then just basically predicting it and then mapping it. That's pretty much it. So how many of them? 20 of them. So let's go ahead and do that, and this should give us a nice picture. Ooh, nice. You see how it's going from 1 to 5 to 0 and then 0 to 6. Remember we picked the values here before, right around here. And then it's going from 0 to 6 to 5 to 8, and ones are warping. I don't see much of any gap right there. Do we get gaps if we go from -5? Because you see some of the gaps means that vector doesn't exist. You get noise. I want to show that noise. Hopefully I can. Okay, let's go from -5 to 5, -5 to 5, and do this one more time. Okay, you see some of this is a bit noisy. It's not clear. In fact, I think we did a great job down here. You see some of this is noisy. We are not getting anything realistic. In fact, maybe for that, again, if you're still around, let's go ahead and try a value of 6 and 6. What happens if I do 6 and 6, which doesn't exist, right? 6 and 6. Oh, actually it's up there. I want to do down here 6 and -6. Okay, 6 and -6. So we should get something noisy, maybe something that looks like 9 but not really 9. Okay, yeah, there you go. You see, this is what I mean. It's kind of down here. We don't have much of a sampling around that area, and if I just give some ridiculous value here, all I'm going to see is some noise. Okay, so let's get back to our noise. -3, 3 and -3 or something. I can play with this all day long, by the way. Now the fun part here, actually, in fact, let's go back to 0 and -1 or something, so it looks good. The fun part is, instead of doing this on MNIST dataset, I don't know what's going on. I may have messed up something, but anyway, so instead of doing this, oh, I didn't select the entire thing. Sorry about that. I got distracted there. Okay, on MNIST dataset, I'll see if I can do that. I tried to download the dataset, which is pretty humongous, but there is a dataset called Movie Star dataset. I haven't played with that. And you download that, it's got 70,000 plus images. I think they're relatively large, but very well annotated. It says like, okay, is this a male or a female? Female with makeup and lipstick, or male with a sunglasses or bald head, or all that kind of attributes. So what happens is when you train it on this latent space, you get like sunglass area, and then you get like female, and you get this and this and this, and now you can actually go from one to the other, and you can actually for example, if you only want sunglass and then this, you can subtract one from the other and add that, so you can add sunglasses to your to your movie stars. Okay, or a smile to your movie stars. This is the type of stuff that people do with the variational autoencoders. It's fun, but we just have to find time to do that. And if I have experimented with that, and if I got some decent results, and I'll definitely create a video on that topic. Until then, please go ahead and subscribe to my channel. It definitely keeps me very encouraged. Thank you.